All right, so we have actually discussed homotopy and the fundamental group. Now, I've gone off script from the book a little bit. I mean, Gilmore does discuss this, and he does describe how these homotopy groups work. We went into a bit more detail. We kind of did some of the formalism showing that a homotopy H was, a function of two variables, S and T, right, where we kind of, I think we took T to be our metaphorical time, although these are really just abstract parameters that go from 0 to 1, actually the closed interval from 0 to 1. So we took some time to discuss all of that. And it was good. Now we are going to actually kind of apply it. What was really interesting to me when I first learned this was that, if you have, say, a piece of a plane, right, and you are missing a single point out of the plane, right? You have, we can even make it more obvious, right? We could make it sort of an annulus type of situation where you maybe treat it like you're missing a hole you've got a hole in the plane. Once you've done that, the homotopy or the fundamental group of the plane, without the hole, it's just the fundamental group is simply the identity. I'm having a little trouble with this new pen. And that's the simplest possible group you could ever get. It is the most absolutely trivial homotopy group possible, fundamental group possible. But as soon as you put in this little hole, as soon as you make this punctured hole, now the homotopy group goes to the abelian group of the integers, Z, right? That one little thing changes a group from complete triviality to actually a group with an infinite number of elements. And an abelian group, so I guess when I think of an abelian group, I think, it's not too complex of a group, it's abelian. But abelian groups can really rack up some interesting elements to them, really interesting complexities. The torus, which is a relatively simple object, has a fundamental group of Z cross Z, which is even harder. So it's like you go from 0 to 100 miles per hour with just one omitted point. I've drawn it here as though it's an omitted space, but all it has to really be is an omitted point, right? One omitted point and kaboom. It goes from the trivial group to 100 miles per hour group, the group of integers. So the question kind of comes up is there something in between, right? Is there some sort of topological space that has a fundamental group that's more than trivial, but it's some finite, discrete finite group that is much less than Z? And that's what's so interesting about what we've been studying, is because the answer is yes, in fact, there is. Let's go back to and which is sort of why we're doing this whole thing. Let's go back to our matrix that describes every element of the group SO3 and every element of the group SU2. So we're dealing with these two different groups. These are not the same group. They did share the same Lie algebra, however, right? So that was interesting. But they're not the same group. And there's one of these reasons we're going to prove that they are not the same group today, is because one thing we know about homotopy and the fundamental group is that they are topological invariants. And topological invariants are really, really big deals. If you discovered a topological invariant, it would probably get named after you, right? It's a very, very cool thing. But a topological invariant is something that is preserved under a homeomorphic mapping. And we're going to take a few minutes to review this. You could skip ahead if you're very comfortable with the notion of homeomorphic mappings, but this is a good chance to dive into topology. I think every time you have a chance to review something, it's worth a rough review, because we remember and we forget, and it's just important to just go through these things over a bunch of times. So let's have a quick look at what we mean by preserved by a homeomorphic mapping. So let's begin by just remembering the topological notion of continuity and why it's so important. We start with two arbitrary sets, X and Y, and I'm going to just symbolize them by these sort of circular areas, because that's just how we do it. We always kind of think of arbitrary sets as regions of the plane because that's kind of where our mind goes. But remember, we don't have any sense of distance or connectivity yet. It's just a set of elements. But once we decide that X is a topological space, that means we give X and Y likewise. We give X and Y what's called a topology. And a topology is a massive set that defines all of the open sets on these two sets, right? So the topology of X is a set of subsets of the set X, and you should know a little bit about that by now. But we now have two topological spaces, X and Y. The difference being it's a set plus a topology, a set plus a topology. Now, once you have two sets, you can do the obvious, well, there's nothing obvious about this, but you can introduce a function which we'll call f that takes elements of the set X and returns elements of the set Y. And right now what we want to do is we want to find a special class of functions that are what we call continuous. Right? We are after a continuous function f. So what could we possibly mean by a continuous function f? Well, if we didn't have a topology, the only things we could really talk about would be can you take a point A and can you generate a point f of A, right? Call that point right here. And is it true that, say, for every other point B, f of B does not equal f of A, right? In that case, what we have is a function that is 1 to 1, right? Every point in the set X generates a unique point in the set Y. But then you could ask the question, so you would never have, for example, a circumstance where B maps to the same point. So f of B would equal f of A. You don't have that circumstance. So you could talk about one-to-one functions without much trouble. And you can also talk about functions that are injective or surjective. Well, you could talk about functions that are onto, right? Does the set X through this function f map into the entire set Y, right? You can imagine it being one-to-one, but not onto, right? So that would be on to if the entire set X maps into the entire set Y. If it instead just mapped into some region of the set Y, it would not be onto. So there's two words for this. There is the key words for this are surjective and injective, right? If you're onto, it's also called surjective. If you're one-to-one, it's called injective. If you're surjective and injective, then you are called bijective. Right? So you can talk about those principles without a topology, right? You do not need a topological spaces to talk about injectivity, surjectivity, or bijectivity. But once you have a topology, now you can start asking other questions, right? You can ask the question, well, what if I have an open set in X, right? And I want to look at what does that set look like in Y? So I'll call this open set, say, U. What is f of U, right? Is f of U open in Y, right? If I say U is an element of the topology of X, can I say that f of U is an element of the topology of Y? Now remember, f is an arbitrary function, right? So this does not have to be the case, right? This is a topological space, but it's certainly not true that any function is going to take an open set in X and give you an open set in Y. If it did, that would be a very special property. And in fact, that property is called being open, right? So we would say that if this property was filled, then f would be an open function. I guess you would call it an open function, right? And so that's interesting, right? Could that be the case? You could also do the same thing for closed functions. It's roughly equivalent, and we'll just do it for open functions. Then we could also ask questions about f inverse, right? We could say, does f inverse have this property? If f is open, is f inverse open? The answer is not necessarily. Once we know about f, we can ask questions about f inverse. We could have asked these questions too, by the way. If it's bijective, if we have a bijective function, we have a very nice invertible function, right? Every point here can be inverted back to a single point in x. Every point in y can be brought to a single point in x. But you can ask all those questions. But now that you have topological spaces, you can ask those questions about open sets, right? So the way we deal with this, or the way we start experimenting with this and generalizing the idea of continuity, is we define continuity, and I'll just review the definition of topological continuity very quickly here. If you know all this, you can skip ahead. But the idea is basically that I'm going to take a point, let me do some erasing here. So we'll take a point in X, right? Call that point A. And then, of course, because we have a function, there is some point in Y, which we will call f of A. Now, the way we define continuity is using this, I'm going to use this so-called neighborhood definition. I'm going to pick an arbitrary open set. This is an arbitrary open set, which I'm going to call V. And V is open. The way we write open is V is an element of the topology of Y, right? This should be a capital Y. V is an element of the topology of Y, which means V is a set, right? You can't think of it as a point. I mean, it's sort of a point in the space of the topology, I suppose, but it's really an open set. It's a subset of Y that, as a subset, is an element of the topology of Y, which is a set of sets, right? If you don't understand that, then this is a little bit too ahead of you. This is a quick review of continuity, right? Not a first lesson. So we pick an arbitrary open set of Y with whose own, well, it's arbitrary in the sense that as long as it contains f of A, I don't care what open set it is. It could be the one I just drew. It could be this one. It could be this one here, like that. It could be the union of this and that, right? It could be any of those, as long as it's an open set that contains f of A. So I can now ask the question, now that I have topological spaces, I can ask the question, is there an open set surrounding the point A in X, such, and I'll call that open set U, right? Is there an open set A, open set U that contains the point A, the domain point A, such that f of U is entirely inside the arbitrary open set V that I've picked, right? So this is now f of U. That blue thing is now f of U, right? Now the point is if this is true for any open set I pick V, any open set V, arbitrarily chosen with the only requirement that it contains f of A, if I can always find an open set U, such that f of U is contained in V. So this U is an element of the topology of X. That's very important. The U is open, right? U is an open set in X. If I can always find that open set in X, so that whose image is contained in an arbitrarily chosen open set of V, this is continuous. And now the idea, of course, if you use a sort of plane idea, V starts getting smaller and smaller and smaller, right? V can be a very, very tiny open set surrounding f of A. But we don't really know what tiny means, but it's, I guess, the idea being that no matter what we choose, no matter, and using this plane model, we kind of get a sense, a smaller and smaller circle around this point. There's always going to be a smaller and smaller open set in the topology of X that will still be inside V, no matter what we choose, right? Okay, the bottom line is, if that's the case, we say that f, not f inverse, but f is a continuous function. So that this definition of continuity, I think if you kind of looked at it historically, would have started with this notion of epsilon delta for functions on the real line. You know, real analysis has these epsilon delta proofs of limits, and epsilon and delta are also ways of defining continuity. But but when you abstractify it to any set, what you need to do, well, first of all, continuity doesn't even make sense unless you're dealing with a topological space, right? You have to have a topological space for any of this to make any, to be logical or to be meaningful. So you have to organize basically a topology is a way of organizing the points of these sets. So it turns out that there's an equivalent definition of continuity. I mean, in topology, there's always like dozens of ways of saying the same thing. It's a big mess. It's very hard to organize all of the thoughts in topology. One kid did it though. Let me put up his webpage. Hold on. Check this page out. This kid, I call him a kid because he seemed to, at the time he did it at least, he seemed to be an undergraduate. He actually organized all of topology at the undergraduate level, even a little bit at the graduate level, in a beautiful, beautiful way on this page, mathonline.wikidot.com. It's called Math on, that's it. And you'll get to this amazing page. You click on the topology link and you'll see all of this very, very well organized. But back to work, an equivalent definition, though, which is beautifully simple compared to what we just did, although what we just did is not too tough. But an equivalent statement that f is continuous is to say that f inverse is open, right? Remember I said a moment ago, if a function takes open sets from x and delivers you always open sets in y, then we say f is open. Well, for continuity, f does not have to be open. F does not have to be open. F can be continuous and not be open. What's interesting, however, is that if f is continuous, f inverse will be open, right? And just as a sampling of how topological proofs are done, let's look at the proof of that, just to kind of see how, just to feel that, go back to that difficult, strict logic of proofs in point set topology. All right, so first, let me take everything we've got here, and I'm going to put it aside as something we can remember. This is sort of our definition of continuity. All right, so I'm going to put that over here so we can remember it. Okay, so we're going to start. We have the topological space X, the topological space Y. We have a function f, which we are assuming is continuous, right? So f satisfies all of the stuff we just talked about. So f is continuous. Now we're going to ask a question about f inverse. So let's start with an open set in Y, right? We'll call it V, right? And so inside V, right, there's going to be, well, let's see, V has an image, right? That image of V over in X will be, I'll just draw it, I'll draw it in green also because it's sort of the same thing, right? This will be F inverse of V. Notice we're treating F inverse and F, they're both functions from one set to another. The fact that they happen to be inverse is just a neat relation between them, but there's nothing unique about the function f. F inverse has an inverse, right? F inverse inverse, and so the point being that we can now treat f inverse as a function. We can even ask about the continuity of f inverse. In fact, that's pretty important. But anyway, we know that we have the image of V, right? The image of V under f inverse is this space over here. Okay, so let's see, how does this go? So we pick a point in f inverse. Oops, I lost a parenthesis. We pick a point in f inverse, and we're going to call it B. And we know that f of B lies inside of V, right? But we also know that V is an open set, right? V is open by hypothesis, right? V is an element of the topology of Y. So if f of B is inside V, right? And if B itself is inside of f inverse of V, then clearly f of B is inside of V. But V is an open set. So it's an important point to remember. This is why doing these proofs is good, because you get to remember all of these facts that you may have forgotten. But one really important property of an open set is that V being open is equal to its own interior, right? Every point of V is in the interior of V. And that's critical, because what that tells us right away is that there's a neighborhood around f of B that is totally inside of V. Because every open set contains a neighborhood of every one of its points. That's a fundamental principle of being an open set. So I can write that there's some neighborhood of f of b. I guess I'll follow the lead of the proof that I read about it. I'll call it v of f of, not a, whoops, v of f of b is a subset of v. And of course, f of b is an element of that little subset of b. So notice we've got this sort of string. V is an open set that we've projected back into x using f inverse. V is an open set of y that is now, who has an image, f inverse of v, in x. We take a single point of the image and project it back and call it f of b, and then we realize, okay, there's got to be a neighborhood around that point because v is open. By the very definition of v being open, there must be a neighborhood around f of b that's contained in v, and that's what we call v of f of b, and we know that it contains the point f of b. So it's a neighborhood of f. This part says v of f of b is a neighborhood of f of b, and it's a subset of the open set we're talking about. It's a subset of the open set v. So I think I'm going to have to draw that in there, right? I'm going to have to actually draw that. So let me get rid of this, and then I'm going to draw v of f of b with this little dotted line here, right? So that little dotted line is v of f of b, which is an open neighborhood of f of b. Now we use the fact that f is continuous, right? If f is continuous, we know that for every open neighborhood that contains a point fb, we know that there is definitely an open neighborhood containing b such that the continuous function f of this open neighborhood is entirely contained in that open neighborhood. In other words, I know that there is some open neighborhood here around b such that, let's see, I guess I have to give that a name, so I'll call that u. And I know that f of u has got to be inside of vf of b. I know that that's got to be f of u has got to be inside vf of b. That's by the definition of f being continuous. That was this stuff we did here. Well, if that's the case, right, then I now have an open neighborhood around b. But I can do this process for every single point inside of f inverse. I can always do this. I can always find v f of b by the definition of the fact that v is open. I can always find a neighborhood around every single point inside f inverse of v, such that that neighborhood is inside the other selected neighborhood because f is continuous. And the reason that that's important is that means that this set, f inverse v, is going to be the union of every one of those neighborhoods around every single point in its interior, right? And that means that f of b is the union of a bunch of open sets, right? An infinite number of open sets. And if you're the union of a bunch of open sets, you're open. Therefore, f inverse of v must be open. That's the kind of topological logic where, we use continuity by the definition of continuity, and we use the fact that open sets are equal to their interiors. You got to remember all of these crazy definitions to keep track of how these proofs work. But there you have it. So that is our proof that f inverse is always open. However, it's a proof that if f is continuous, then f inverse is always open. Now the question is, well, wait a minute, what if f inverse is always open? Does that mean f is continuous? So these proofs are if and only if. They have to go both ways. So to show the other direction, we will take an arbitrary open, so Y is a topological space, right? Y is a topological space. So we imagine that we have some base for the topology of Y, right? So the topology of Y has a base, and we'll call that base, I guess we'll call it B of Y, right? So BY, that's a subset of the topology of Y, right? But it's a base. So every element of the topology of Y can be constructed from this base. Yet another topological concept that you have to review to understand these proofs. And that's what the undergraduate course in topology does, is it just covers all of these definitions and concepts. So by presumption, we are now going to assume that F inverse is open, right? We're going to make that assumption. F inverse is open. Therefore, F of any member of the base is, or F inverse of any member of the base is a set over here. I'll erase this. So let's see. This is, say, call that a member of the base B. Then F inverse of B, that's open. F inverse of B is an element of the topology of X because we're assuming that F inverse is open. All right, so considering that, let me erase some stuff here. Considering that, let us consider one particular point. I guess we'll do the same thing. We'll have this point, call it A, and then over here we have F of A. And now we look at every element of the basis of the topology of Y that contains F of A, right? Every element of the basis of the topology of Y that contains F of A. This is called a local basis of the point F of A. So the way I have it written here is BY is the basis of the topological space Y, and that's a subset of the topology of Y. In principle, by the way, this could be, sometimes the basis is the topology, right? So we can have a little equal sign there. It doesn't have to be a proper subset. And then our example is the B is just one element of the basis. And we always know that the image of every open set is open under F inverse by our hypothesis that F inverse is open. And so F inverse of B will always be an element of the topology of Y. Notice I haven't said anything about the basis of X, just the topology of X. F inverse of B is an element of the topology of X, right? Now we take F of A, so there's a point A in X, F is continuous, so we have, well, F is a function, so we have F of A. We don't know that F is continuous, right? F being continuous is our question, right? That's our question. We know that it's F inverse is open. We're wondering can we prove that F is continuous? So now we take a point F of A and we create a local basis. So we're taking all of the elements of the basis of the topology of Y that contain A. And that is a local basis. And we'll call that local basis, we'll call that B of F of A, and that's a subset of B of Y. Now I take an arbitrary open set around F of A. I'll call that V. Now, because B of F of A is a local basis, right, I know by the definition of what a local basis is that there is an element of that local basis that is a subset of V, right? A local basis of a point contains the point, and no matter what open set you establish that contains the point, there will be an element of the local basis that is a subset of the arbitrary open set you have chosen. So you will always have an element of the local basis inside this arbitrarily chosen V. So I will call that B, right? So B is now an element of this local basis, and B is guaranteed to be a subset of V. So I've chosen an element of the local basis that is a subset of this open set V, which is an open neighborhood of F of A. And it's guaranteed to exist because we're dealing with a local basis. So now you can almost see what's going to happen. We're going to now look at the image of this open set B that contains F of A under F inverse, right? And F inverse is open. So we're guaranteed to have an open set somewhere over here that is the image of the open set B. It's guaranteed to be open because by assumption, F inverse is open. And we shall draw that open set like this, and we'll call that F inverse of B. And F inverse of B is an element of the topology of X. I've used the same symbol, so I've already got it written here. But wait a minute, we're done, right? Because now I've found an open neighborhood of A such that its image under F is a subset of an arbitrary open set V, right? Guaranteed. There's always going to be this open set around A such that its image, which is going to be B, will always be inside of V. And V was chosen arbitrarily as an open set of an open neighborhood of F of A. So no matter what open neighborhood of F of A I pick, I'm guaranteed that there is an open neighborhood around A that is whose image under F is contained inside it. And that's the definition of continuity. So I've proven, and it was critical that F inverse be open for that to be the case. So I've proven it this way, that if F inverse is open, then F is continuous. But I've also proven that if F is continuous, then F inverse is open. So this is an if and only if, and it's now an equivalent condition that F inverse being open is the same as F being continuous. I guess there is the one last point that in the proof that I have been using to review this. This, of course, only proves that the point is that F is continuous at A. This all depends on, neighborhoods surrounding the point A. But of course, A is arbitrary, right? So A being arbitrary means it's continuous everywhere. So the other important thing to realize before you see how this becomes a homeomorphism is what we're studying is basically how open sets are mapping under the function F. And what's interesting is that open sets under a continuous function map in the opposite direction in an open fashion, meaning open sets in Y under F inverse will map to open sets in X if F is continuous. But that doesn't necessarily mean the other case is true. It does not mean that open sets in X map to open sets in Y. So you could ask the question, well, wait a minute. If F is continuous, then F inverse is open. Is it also possible that F inverse is continuous? Right? Say I wrote F inverse is continuous, right? And then I could write, all I know at that point, the inverse of a continuous function is open. So F would be open, right? There's that circumstance. Let me erase all this just to make sure we're speaking in bigger generalities right now. So a function can have a continuous inverse, but not be continuous. But if that was the case, then the function would have to be an open function. But if a function is continuous, then its inverse will be open. So the obvious question is, wait a minute, what about the case where a function is both open and continuous? Well, if it's open, that means its inverse is continuous. If it's open, that means its inverse is continuous. If it's continuous, that means its inverse is open. So both of these things would have to be true, right? And that's really, really interesting, because what that means is that every open set in X gets mapped under F to an open set in Y, and every open set in Y, likewise, gets mapped back to an open set in X under the inverse. And if in addition to this, so that's really important, because what you're basically doing is you're taking the open sets from one set and you're just morphing them into open sets over here. And for every single open set over here, you have an open set over here, which means the topologies are very similar, right? You can imagine a case where you have a topology in Y that is much, that just is finer in a sense. When you say a topology is coarser or finer, you really have to be comparing topologies within a set. But you can imagine that there would be open sets in Y that that some of them map to open sets in X and others don't, right? In that case, F inverse wouldn't be open, because F inverse to be open has to take every open set in Y and map to an open set in X. So what you're really doing is you're kind of just, once you have a topological space and you have these continuous and open functions, what you're saying is that you're basically taking the topology of X and you're just turning it into the topology of Y directly using this function. And likewise, you're taking the topology of Y and you're turning it into the topology of X. And that's a very strong statement. If in addition to that strong statement, these two functions are one-to-one and onto, which is another way of saying if they're bijective, right? If it's a bijective function, which means it's surjective, injective, which means it's bijective, that is what a homeomorphism is. And these homeomorphic spaces are profoundly related because basically they're the same damn space, right? You found a function that just takes every point here and every open set here and turns it to a point here and an open set here, and everything. It's just it's almost like you're renaming things in a group isomorphism, and you're not really changing anything about the topological structure of X because it's homeomorphic to Y. And in fact, all homeomorphic spaces are pretty much the same from a topological perspective. And by saying they're the same is if you have a homeomorphism, we want to know what makes the spaces the same. Why can I say X is the same as Y? Well, first of all, it's homeomorphic. But the reason that that's important is certain topological properties of X are preserved under homeomorphisms. And of those many topological properties, you have connectedness, you have compactness, you have separability, what else? Countability. You have countability. And each of these has a whole bunch of sub-properties that are all preserved under homeomorphism, which means if this space has a certain kind of connectedness, this space will if they're homeomorphic. Now, what does it mean to be homeomorphic? Well, if any such function exists, if any such function f exists between the space x and y, they're homeomorphic. So to show that x and y are homeomorphic, I need to find a function f that does this. And if I have two spaces and I haven't found a function f, they may or may not be homeomorphic. It depends on whether that f exists. And it's a major mathematical problem to show that two sets are homeomorphic. And if you discover two very different topological spaces being homeomorphic, you've actually made quite a little discovery. And the fact that you haven't found that function doesn't mean doesn't have any impact on whether or not they're homeomorphic. It just means that you don't know. However, you can often show that two spaces are not homeomorphic right away by looking at their properties. And if they have any two of these properties are different, if one is countable and the other isn't, if one is separable and the other isn't, if one is connected and the other isn't, you know right away they're not homeomorphic. Because what makes these guys so important is that they're preserved under bijective and bicontinuous functions, which are called homeomorphic functions. So it's a really, really, really big deal when you discover a property that is preserved under homeomorphisms. That's a topological property. And it's a pretty big deal when you discover that two sets are or are not homeomorphic. There are two sets who might actually seem very similar to us, but it turns out they're not homeomorphic, which means they're actually somewhat dissimilar. Okay, and that's where we reconnect with our study of Lie groups and Lie algebras. So now we can consider our two sets, the sort of this disky thing and this disk with a hole missing. Now I'm using this as a literal set, like in the plane, right? This is no longer an abstract set like we were talking about back here, right? These were abstract sets. Now we're actually talking about subsets of the plane, but this one's got this hole in it. So the question you might ask is, are they homeomorphic, right? Is there a function, a homeomorphic function f, which means f is going to be 1-to-1, it's going to be onto, and f inverse, it's going to be continuous, 1-to-1 and onto, and f inverse is going to also be continuous, right? And if that's the case, then they would be homeomorphic. So we ask the question, is it possible to find such a function where every open set over here kind of blends into all of the open sets over here by just distortion under F, right? This is sort of the idea of turning a sphere into a coffee or a donut into a coffee cup, right? You're just distorting the open sets to a slightly different kind of shape, but you're preserving everything because it's homeomorphic. You're not tearing any open sets. You're not building any open sets. You're just morphing them one to one. Can this be done? Well, the way to check is these topological properties. You look, are they both countable sets under the topologies? Are they connected? Are they compact? Are they separable? And all of those might actually pass the test. But if they all pass the test, that still doesn't mean they're homeomorphic. Just because every known topological property between two sets agree, hell, this is math we're talking about. There's unknown topological properties waiting to be discovered out there in the world of mathematics. So that doesn't do us any good. It certainly makes us suspect that they would be the same. But one thing we did learn is we learned that both of these spaces were path connected, and we knew that if we took loops in these spaces, we could create families of curves in these spaces, and we could build out the fundamental group from these loops, right? The fundamental group. I should do it in a different color. So I take a point A, the fundamental group of this space is the identity. And we know that the fundamental group in this space is the set of integers, z, under addition, right? Because we know that we can kind of go around once or twice. We can not go around at all, which is sort of related to the identity. We did this in our past two lectures. So these two steps have two different fundamental groups, right? Well, that opens up a huge question. Is the fundamental group something that we expect to be preserved under homeomorphisms? Because if the fundamental group is preserved under a homeomorphic mapping, then the fact that these two have different fundamental groups means that regardless of whether you find a function or you don't know of a function, you'll never find a function that's a homeomorphism. There is no homeomorphism because you've shown that a homeomorphically preserved property, the fundamental group namely, is different for these two sets, and therefore there can be no homeomorphism between them. Well, so is the fundamental group a topological property? Well, the answer is yes. The fundamental group is a topological property, and we're going to use that fact to show that SO3 and SU2 are not homeomorphic because they have different fundamental groups. So what we have left on our plate is to prove that the fundamental group of a topological space is in fact preserved under homeomorphisms. And then we are going to show that there is no homeomorphism between SO3 and SU2. And we're going to show that by showing that the fundamental group of SO3 is different than the fundamental group of SU2. So that's where we'll pick up next time. So this has been a pretty quick review of just the notion of homeomorphisms and continuity and topology, just to get that back up to speed, because we're going to talk about continuous functions and things like that quite a bit. We have already, but we're going to keep it up. Okay, I'll see you next time.